Hi everyone, welcome to join this presentation. Today I'd like to introduce one of my research topics in network monitoring. It's about the design and implementation of a bandwidth efficient in-band network telemetry system. This is the outline. First, I will give a quick overview of this work. Next, assuming that most of you are not familiar with computer networks, so I will give a quick introduction to the background of today's programmable networks. Later, I will go through the technical detail to introduce the research motivation, then the design, implementation, and performance evaluation of the system will be illustrated. Finally, I will conclude this work and talk about my future work. This work is about the design and implementation of a network monitoring system. The system is capable of capturing packet-level network state in a nanosecond scale. In a 100 gigabit per second device, there are at least 8 million network reports generated each second. It is hard to process such huge amount of data by a single high-end server. In-network computing is a hot topic in the emerging programmable switch. The system and technique proposed in this work is applicable to real-world problems. A part of this technology was transferred to NCSIST, National Zhongshan Institute of Science and Technology, Zhongkeyuan. The system can reduce the overhead of network reports as much as 4 orders of magnitude compared to existing network telemetry system. This work was published in GlobalCon in Hawaii last year. It cannot be done without the collaboration and efforts of all co-authors. Network telemetry is a process to understanding the network states in the current network environment. Typical network states include transmission delay, transmission latency, which implies the network congestion, unexpected packet loss, and the performance index such as throughput and its degradation. Network telemetry is very important for network administrator and operators. This is because network states are almost the only information source to make decisions for managing network in various perspectives. Network state is the foundation for not only network management, but also traffic engineering, load balancing, flow control, congestion control, and security. As the network bandwidth increased dramatically in recent years, it became much harder to effectively monitor and analyze the network state in real time in a very fine-grained manner. The current network is very hard to monitor and debug. Traditional method relies on sending probe packet and polling counters on device to diagnose networks. It takes round-trip time to get a whole snapshot of the entire network state. In a 1 gigabit per second network, each packet is processed about in 1 nanosecond. The probe packet takes millions seconds to snapshot the network state. It sounds like that it takes 1 million days to check what happened to your neighbor yesterday. Obviously, it's infeasible to send probe packet back to back just for capturing a 50 nanosecond network pulse continuously. Ironically, in the past decades, there is no clever way to check network states, even in a large company such as Goldman Sachs. In-band network telemetry, aka INT, is a method that can observe network states for each packet and each network node the packet is traversing. The topology simulates a subgraph of a typical data center network. The idea of INT is simple. When each packet forwarded into any one of edge switch, the switch inserts network states to the original packet header. The state is carried with the data packet as the packet traversing switches. When the packet is leaving from the edge switch to the end host outside of the INT network, the inserted network state will be extracted as a new INT report packet, and the header of the original packet will be restored. The packet sender and receiver are not aware of any changes in their data packet. The INT report will be transmitted to a dedicated server called INT collector. For each each switch. It can be an int source or int sink, depends on the direction of forwarding packet. Before dive into the technical detail, won't you ask a question? Why does an int exist 20 years ago? Why this technology emerged in recent years? In fact, the record route option was defined in the Internet Protocol specification in 1981, but Rome was closed in a day. In 208, the SDN concept was proposed. The open flow protocol became the de facto standard in modern computer networking. The network switches are managed by a globally logical controller. The packet forwarded between hosts are determined by the match action rules installed in each switch from the controller. However, the switch can only be communicated with each other of the same protocol. The supporting protocol implemented in the switch hardware ASIC, which are limited and fixed. It takes about 3 years to support a new protocol, from proposal, alignment, chip design, to chip mass production. The match action rules are limited by the hardware switch. The requirements of network innovation are huge, but the iteration speed of network devices are slow in such bottom-up design manner. Many vendors try to design programmable switches instead of fixed function and configuration. A top-down approach with specific language that can describe the switch behavior is desired. Many network processors are invented, including NPU network process unit and FPGA-based solution. However, a common challenge is how to balance the flexibility and the performance. The more flexible, the lower performance we can obtain. In recent years, domain-specific processor is becoming popular, from GPU in graphic acceleration, DSP for signal processing, to TPU for machine learning to training model. What about networking? In 2014, reconfiguration switch architecture was proposed. 2 years later, in 2016, P4 switch ASIC was born. P4 stands for Programmable Protocol Independent Packet Processor. It was the fastest switch ASIC in that year, not only flexible enough, but also very performant. The switch chip has 6.5 terabit per second overall throughput. P4 switch can be programmable by P4 program, which is written in P4 language. The P4 language can be compiled into a binary or JSON file that can be used to program the target switch, P4 switch. P4 language is a C, C++-like language. Different switches has different architecture, and so P4 program should include appropriate switch target file. The right-hand side is an example P4 program. It has a main function, and it called server logic switch component and API to define the switch handling logic. PISA is one of the representative P4 switch architecture. It composes of programmable parser, metadata, packet processing pipeline, which composes of match action unit. Each packet enters from parser to go through the packet processing pipeline and the parser at task speed. In each match action unit, there are limited memory and LLU to do very basic and limited operation. Each memory location can only be accessed once in the entire pipeline. The packet header is extracted from the parser, modified in the pipeline, and assembled in the deparser. Each packet has accompanying metadata to store many packet attributes and even network states. Since P4 is a domain-specific language, the P4 language constructs are mapped to target switch components for specific switch architecture. For example, a parser is a state machine for bit field extraction, a table, action, control flow statement mapped to the match action unit in switch pipeline. Left-hand side is a real-world working P4 program. In the IPv4 LPM table, it examines the destination address of IPv4 headers, and one of the three actions will be performed. And each action is a standalone function with or without action data, such as drop and IPv4 forwarding function. P4 code just the skeleton of the logic of the target switch. The right-hand side shows the logical mapping of the key, action name, and the action data. For example, this key map should be mapped to this action name. So when the switch sees this key, and this function will be invoked. When the switch sees this IP range, and this action data will pass to the action function. The actual form of the rules is described in semi-structured data format, such as JSON, not this table. It's just a concept. It's a real match action rule format. Standard int has tens of switch informations. Whenever each packet entering the switch, the network state will be available in Traffic Manager TM. To make packet carry network state, all we need to do is to insert the int instruction bmap before packet entering to the Traffic Manager. Then the Traffic Manager will copy int information to the metadata. The metadata should be appended to the packet header in the egress pipeline. This is how int works in P4 switch. This information can be selected by the int instruction bmap. The research idea was from the day one after we set up our first in-band network telemetry system. We added a fine-grained network state called the rules, and expect it will not introduce too many overhead to the int system. As the packet sent from the left-hand side host forward hop by hop to the right-hand side host, we connect the switch with a 8 commodity server with 8 core and use only 10 gigabit per second link. However, since the INT report, we expect there are 2 gigabit per second throughput in INT report, but we only obtain 100 megabit per second with multi-threaded collector written in C library. About 99% of report were dropped. For resolving this issue, a couple of selections has been proposed. The typical solution is scale out. The deep inside int system proposed by Barefoot Company use 4 high-end rack servers to handle the int report traffic for a single port. We don't consider this solution because 4 servers only serve for one single 100 gigabit per second port is a waste. The cost is too high. Another solution is to filter int report on the server side. It means that the server should parse all the int report packet and determine which report is meaningful and store them to databases. Each packet should be parsed by the server's CPU resources. Some of these methods use kernel bypass mechanism. However, CPU is not the optimal place to parse packet. Parsing packet usually needs loop unrolling in kernel, and which may consume too much kernel resources. The third kind of solution for controlling int report is to control the int report generation rate in the switch directly. The author determines which report is significant or not in a specific time range. It brought an outside-of-box idea compared with previous 2 methods. However, there are many limitations in switches. For example, this method requires a timer, but P4 hardware switch doesn't support this kind of timer. It can only be realized in simulator. So this method is not realized in the real-world switch. This is a summary table of existing methods. Deep inside scale out is expensive. Int monitor, collector, and primethers have a very high report processing overhead. Int collector relies on kernel pass-through features which does not scale well. Selective int is impractical for real-world hardware switch. This is our solution, which is simple. We try to reduce the int report directly in the hardware switch. There are several benefits. First, the switch is the best place to parse the data packet. A dedicated parser implemented in hardware ASIC is much more performant than any other packet processing method on CPU. Second, we use switch to filter report can reduce the usage of external CPU to process the int reports. Moreover, the bandwidth requirement between the int sink and the collector can be greatly reduced. And of course, we can apply our hardware achievable method on this solution. It's hard to develop a complex feature with limited computation hardware switch. The hardware switch provide operation capability, for example, ALU, which can only support 2 expressions. It means you can only do A plus B or A minus B, but you cannot do A plus B multiply C. So it's very hard to program with the switch hardware. Besides, there is no direct way to do flow point calculation. Next, the RAM of the switch is limited, so it cannot store too many packet information. Moreover, the register of each ALU can only be accessed one time. That is, when you have an array, you can only read, write, or both rewrite a specific offset each time for each packet. Therefore, a good strategy is important and precious. Our strategy should be simple and effective. We hash the flow packet header, store them in the register, and filter int report by detecting stage changes. We have 2 types of stage changes detection method. One is for numerical state, which can be subtracted. If the result is not 0, it means the stage changes. We have threshold-based state detector, which provide a single or a pair of boundary to check if the network state exceeds our expectation or not. One of an important goal is to make our enhancement transparent to the original system. 5-tuple is a very basic terminology referring to transport layer packet. We use the built-in hash function provided by the switch to represent the flow as a numerical value called flow ID. 5-tuple and the int report are also hashed in our system. Okay, there are some guidelines about good system design enhancement. It should be a very thin layer to the original system. The mechanism should be as transparent to the original system as possible, and it should introduce as few as overhead. Our design goal is not to change the original relationship between int compliant devices, but to reduce and filter report directly in the P4 hardware switch. This is the actual whole picture of our system architecture. We not only build bandwidth-efficient int mechanism on existing switches, but also build an analytic platform to provide more features, help fulfill network monitoring requirements. The filtered int report will be stored to a time series database called InfluxDB, and then we can trace both real-time and historical data. This is the web UI view. We can see a switch topology. It is rendered by a JavaScript library called view2vis in real time. There are 2 other views for path tracking, and rule matching. In this page, we can see the packet flowing path by the both ranged or real-time window. The flow pane shows the most recent flow in the network. Although this example only shows 2 hubs, switch 3 to switch 2. But this system is very useful when the topology is large and complex. The rule ID is used to identify action function written in the P4 and management by the controller. It's an amazing mechanism to help programmer and network administrator to know how their rules are matched by different packets. Here we can see that the rule 274 and 271 are matched by this flow. Our system is the first dynamic match rule management and visualization system. In other systems, such as Barefoot's Deep Insight, they can only show hard-coded rules. In contrast, our rules can be any action. So the P4 developer can use our environment to debug their code easily. Otherwise, they can only use a tool provided by the switch vendor to dump snapshot by snapshot to see what's wrong with their P4 code. The rule matching visualization can also help administrator to detect if the match action rules are hacked. According to NCSIST's researchers, some hackers may insert malicious rules to mirror packet to an unexpected destination. We extend the standard int bitmap by adding a bit to tackle the rule tracking feature. The offset of the bit is reserved originally, so this augmentation should not bring any trouble to the standard int. This is a quick recap of our int system. The goal is to add logic to the int sync switch to reduce the int report traffic generation rate. I will not only show our int sync flow, but also show how we design the int source and int transit switch. Let's get started. When a packet is entering from the edge switch initially, the switch should be treated as int source. It should adjust the original packet header to concatenate int headers. In standard int protocol, there is a shim header for storing standard IP packets reserved bit. As we mentioned previously, after adding shim headers, the network state information can then be added to the header as metadata. This is the logic of int transit. It's simple. It just append more network states to the int headers. The traffic reduction flow will be triggered when the packet is forwarded out of the edge switch. We first check if the packet header is a legal int. Then we compare the packet's belonging hash value of int report with previous packet according to its network state type, numerical or threshold based. We only clone and forward the packet to collector for significant change. For those packets that are not changed or with only minor changes, we increment a special counter called CMS count sketch. The packet counter will be regularly flashed by a special switch packet generation module and sent to collector as well. So our collector should recognize 2 types of int report, full version network state and the counter version network state. This can help to avoid the packet-driven nature behavior of P4 switch to miss capturing the little change of packet counts. We evaluate our system with 3 100 gigabit per second P4 switches and 8 commodity desktop as our server. We only have a pair of special NIC card which is powered by DPDK and it can transmit packet in 100 gigabit per second. We use DPDK as our main traffic source and send other traffics in 10 gigabit fiber wire due to the limitation of server resources. This is our P4 hardware switch and this is our servers. Each server connected with switch by fiber cables. Due to the limitation of network resources, we can only generate limited flow in limited speed. To ensure that each switch are working under the same condition, we keep our overall aggregated traffic as 101 gigabit per second by varying the throughput on normal host and DPDK. We measure the performance of our system by using a metric called traffic reduction ratio. R equals to M divided by N. N is number of inter-repo with traffic reduction. M is number of repo without traffic reduction. X and Y are used in numerical network state traffic reduction. X is the change period of the network state. We use rule as change as our change source. Y is the number of affected flow in rule change period. In our numerical measurement with our traffic, there are 8 million packets per second generated. The best case is X equals to 0.015625 and Y equals to 10. There are only 640 packets inter-repo generated. The traffic reduction ratio is equal to 12,500, which is 4 orders of magnitude improvement. In threshold-based network state traffic reduction, we measure the rate of inter-repo that were generated when our system detected that there was a significant change in hop latency. 3 different threshold values for hop latency were used, 1, 2, and 5 microseconds respectively. The result shows the rate of generated inter-repo under different numbers of greedy TCP flow when 1, 2, 5 microseconds were used for traffic reduction threshold respectively. This figure shows the traffic reduction ratio, which are obtained by dividing 8,000 kpps by rates reported in previous figure. The original rate of 8,000 kpps when our traffic reduction scheme was not used. We can see that when 1 to 5 microseconds were used as the threshold, our int system could reduce the rate of generated inter-repo by a factor of 2,439 respectively. In conclusion, we design and implement a bandwidth-efficient int system. It greatly saves the network bandwidth consumed by inter-repo. It also avoids server processing unchanged network state. This system is capable of monitoring subtle network state change in real time with simple but effective design strategy. Through this work, our research team has a good understanding of P4 hardware switch architecture and have a good foundation in network state management. Our team is using these experiments and the knowledge to develop fine-grained traffic engineering methods. And let's conclude this presentation. Thank you very much for your attention.